Welcome to our talk. My name is Heinke Hien, and it is my pleasure to talk about our recent work on hierarchical expert networks for meta-learning. So in meta-learning, the task is not to only learn a single problem, to solve a single problem, but rather to solve a set of problems. So imagine you're trying to solve how to identify characters, hand-drawn characters, and you have only few of them. And our idea is that if you can identify sub-regions of this problem set and train specialized decision makers on each of the sub-problem, then they can process information very efficiently, meaning that they can adapt more efficient and within fewer iterations than an agent that is trying to solve the whole problem at once. And we tackle this problem in the following way. We devise a hierarchical system that uses a latent representation of a training data set found in several ways. For example, for pictures, we use an autoencoder and the latent representation. Then we feed this latent representation into a selection network, which picks one of the expert networks that are usually very small and also have a decision that have a deliberation cost measured as the DKL between the agent's prior strategy and its posterior strategy. And we will see that if we penalize deviation from a prior strategy, this will drive specialization in the decision maker because it cannot afford to change its strategy very often and has to stay close to the prior strategy, meaning the strategy that works well enough for the complete sub-region that is assigned to this expert. So we have this objective here. We're trying to solve a maximum utility problem, expected maximum utility problem, and we have a cost in selecting an expert, and we have a cost as measured as the mutual information for selecting an expert, for selecting an action given an expert M and given a specific input. So we have two kinds of information processing costs. And if you were to apply this to a specific problem, then the expected utility problem that we're trying to solve becomes maybe a classification problem, as in this case. So the selections stage would be fed with a complete training data set. Then we select an expert M, which we train like this on the data set. And then we evaluate on a similar but different validation data set. So the selection stage basically optimizes how to select experts that have been shown to specialize on data, meaning that their posterior strategy is close to the prior strategy for a specific data point. And we applied this, we evaluated this on the OmniGlow few-shot classification data set. We considered several baselines. One is pre-training of a shallow neural network with only one convolutional layer. And we trained this network naively once with MAML and once with matching nets. Compared this to how would they fare if we use 4 hidden layers as suggested in the original papers. And then we compared this to our network, which has maybe here in this case 8 experts or 16 experts. Again, each of them only a shallow neural network with one hidden convolutional layer. And we can see that we combine several of them. Obviously, we can outperform the pre-training data, but we can also outperform the MAML baselines on one single shallow neural network, and we achieve comparable results to using 4 convolutional layers in MAML and matching networks. We also tried this out. We also evaluated this out in meta reinforcement learning problems, where our setup is the following. We have a double-linked inverted pendulum that changes its parameters each episode. So after one episode is done, it changes the parameters. So maybe the torque or the length of the links, the weight of the links, the reward function is also changed. And then we try to evaluate our agent that has learned on an old parameter setting for the double-linked pendulum. So obviously, if you use one single learner, like in this case here, it's almost impossible to solve the task. But as soon as we have two experts that can specialize on certain parameter setting, it gets better, and we can also achieve with 4 experts that are again shallow neural networks. We can achieve similar performance to proximal meta-policy search and MAML, which we have used as a baseline again here. So here we plot how the experts can adapt to a specific meta task that it has not seen before. So if you have one expert can not adapt at all, basically. But as soon as we have 2, 3, or 4, they can adapt more quickly, and they can also process more information the more experts we have, because they specialize more, meaning that their prior policy gets better and better adapted to specific parametric settings of the double-linked pendulum. So to conclude, we have introduced a method that is principled in the way that it comes from one optimization problem, one optimization setting, and our main hypothesis is that resource limitation drives specialization, which in turn gives rise to meta-learning problems. And one open question is, for example, that how can we transfer this to arbitrary high dimensions? Because for the omnigals, for example, we only use binary classification problems, so n equals 2 in an nk setting. And how can we use more than one hierarchy level? Thank you. Looking forward for the questions.